Hello everyone, welcome to this week's lecture. Today we're going to talk about ANOVA, which is used to study the association between a continuous variable and a categorical variable with more than two categories. I will walk you through examples of the test. At the end of the lecture, you will know how to perform the test and how to draw a conclusion from the test result. First, let's do a bit of recap of what we learned from previous lecture. We covered the two sample t-test, which is used to compare the means of two groups. In other words, to study the association between a continuous variable and a categorical variable with only two levels or categories. However, if the categorical variable has more than two categories, what can we do about it? Can you think of some examples where the categorical variable may have more than two groups? Here, I list some examples of analysis. Can you pick the ones which involves a numerical response variable and explanatory categorical variable with more than two categories? You can pause for a few seconds and continue playing after you choose your answer. Okay, so here, the correct answer is B. Now let's talk about all these options. So option A is, does work status predict suicide among Ontario adults? In this scenario, the explanatory variable is work status, and it has three different categories, which is unemployed, employed full-time, and employed part-time. And in this scenario, the response variable is suicide. This is a binary categorical variable. So in this case, we have two categorical variables. So the best option for this scenario is chi-square test, as we already learned in this class. For option B, it's about the air quality differed by different Toronto area. In this case, the response variable is air quality, which is concentration in parts per million of particulate matter. So this is a numerical variable. And the explanatory variable here is Toronto area. So it has different values like York, East York, Etobicoke, or Scarborough area, and etc. So this is an categorical variable with more than two categories. So this is the correct answer for this question. For scenario C, is blood iron concentration related to the amount of iron in diet? The explanatory variable is the amount of iron in diet. So this is a numerical variable, and the response variable is the blood iron concentration, which is also a numerical variable. So in this scenario, we have two numerical variables here. For this scenario, we'll need to use the correlation or regression for the analysis, which we will learn in next week. For scenario D, does bacterial growth on cephalosporin-treated agar differ by wild types versus mutants? In this case, the response variable is the bacterial growth, which is usually measured as the number of colonies present on the agar. And the explanatory variable is two category wild type versus mutants. So here we have a categorical variable with only two levels, and we have the response variable as the numerical variable. So the test we can use for this scenario is t-test, which we already learned in class. Okay, so when we have a continuous variable and the explanatory variable as a categorical variable with more than two levels, the hypothesis test we can use is ANOVA. The full name of ANOVA is the analysis of variance. It's used for a continuous variable and a categorical variable with more than two categories. What it does is it compares the means of more than two groups and tells if any of the two or more means is different from any other. So what will be the null hypothesis for ANOVA? And because we are comparing the means across different groups, the null hypothesis is the mean across all groups are equal, or we can also say all groups have the same mean. For the alternative hypothesis, we can say not all means are equal, or at least one mean is different. To show this on the graph, the figure on the top shows the situation for null hypothesis. We can see the means of the three groups are quite close to each other and they're almost identical. However, in the figure at the bottom, the means of the three groups are far from each other, especially the red curve. Okay, so just a quick note here. If you do an ANOVA with only two groups, mathematically, it is the same as the two-tailed two-sample t-test. Now let's use an example to show how ANOVA works. Say we want to study the relationship between commute time to campus and the residential area. We take a sample of the Ryerson students and ask them to report how long it takes for them to get to the campus. Based on their residential area, we put them into three categories: downtown Toronto, outer Toronto, and other GTA area. The collected data are shown on these figures, where the x-axis shows the three residential area and the y-axis represents the commute time to campus. Each dot represents a student, and the color of the dot shows its residential area, where red means the other GTA area, blue is outer Toronto, and the orange is downtown Toronto area. So first, let's focus on the figure on the left. So it's this one. In this figure, let's first ignore the different residential areas of the students and treat them as a whole group. The black line here, this one, is the overall or the grand mean of the entire sample. And the distance between the dots and the grand mean, so it's this distance between the dots and the grand mean, represents the variance of the entire sample. Now let's go to the graph in the middle with caption groups. So it's this figure. So besides the black line, this one, the grand mean, the three short red lines, these ones, shows the mean for each residential group and the distance between the three red lines and the black line. So it's this distance is the variance between groups. Lastly, let's go to the figure on the right with caption arrow. So it's this figure. It shows the distance between the dots and the three red lines. So it's this distance. This distance represents the variance within the groups. So it's the variance within these three groups. Okay, to sum up, the variance of the entire group, which is the figure on the left, is the sum of the variance between groups, which is the figure in the middle, and the variance within the groups, which is the figure on the right. Again, so the sum So the variance of the entire sample is the sum of the variance between groups and the variance within groups. So having this as the background knowledge, the purpose of the ANOVA is to compare the variance between groups to the variance within groups. To do so, we calculate test statistics, the F ratio. Basically, it is the between groups variance over the within groups variance. After the F value is calculated, we compare this calculated F ratio to a critical value from the F distribution table, which we will talk about later. And by doing this comparison, we're able to tell whether the null hypothesis is true or not. The formula table here shows the entire process of conducting our ANOVA test. Now let's take a closer look at the table. So we can start from the first row here. So this part shows the variance between groups, and we call this the group. And to do the calculation of the variance for this part, we start with calculating the SS, which is the sum of squares. And the second step is to calculate the DF, the degree of freedom. And finally, with the calculated SS and the DF, we can calculate the mean squares, MS. Okay, so now let's look at the detailed formula. To calculate the sum of squares between groups, the SS group, it equals to sigma ni times bracket yi bar minus y bar bracket squared. In this formula, ni is the sample size in group I, and yi bar is the mean in group I, and the y bar is the grand mean, which is the mean of the entire sample. And the formula for the DF is k minus 1. In here, k is the number of groups. So for example, if you have like a categorical variable with 3 categories, that means you have 3 different groups. So your k will be 3, and the degree of freedom for the group will be 3 minus 1, which is 2. Okay, and to calculate the mean squares of group, you just need to divide the SS group by DF group. Okay, and the second row here, the arrow row, this one shows the steps to calculate variance within the groups, and we call this variance is the arrow. And also similar to what we do for the between groups variance, we started with calculation of the SS arrow as well, but the formula is a bit different. So it's the sigma SI squared times bracket NI minus 1. So here, SI is the standard deviation in group I, and the NI is also the sample size in group I. And the degree of freedom arrow is the N minus K, where N is the sample size of the entire group, and K is still the number of groups. And also the mean squares for the arrow group is still SS arrow divided by degree of freedom arrow. And for the total part, so this one is the variance of the entire sample, and the SS total is just the sum of SS group and SS arrow, and the degree of freedom is N minus 1, which is the total number of samples minus 1. And after we calculate the MS group and the MS arrow, then the F ratio is calculated as MS group divided by MS arrow. So this is the F ratio we need to calculate. Once we calculate the F ratio, then we will need to go to the F distribution table to find out the p-value, whether it's larger or smaller than our alpha, which is the significant level. Then based on that, we will be able to make a conclusion on whether to reject or fail to reject the null hypothesis. It's a bit overwhelming only looking at those formulas. Now let's walk through an example which will help you better understanding the entire process. In this imaginary example, we measure the temperature in 3 different swimming pools in Toronto, and we want to know whether the temperature is different among the pools. Okay, so here we summarize the temperature measurements we got from the 3 pools. The response variable, temperature, is measured in the unit of degrees Celsius. It's a continuous variable. And the explanatory variable is the different swimming pool. So here we have swimming pool A, B, C. It's a categorical variable with 3 categories. So the most suitable test here is ANOVA. Now let's do this ANOVA test together. To do our ANOVA test, we can start with forming our null hypothesis and alternative hypothesis. So for this scenario, we just want to compare the means between different pools, and we want to know whether they're the same or not. So the null hypothesis is the mean temperature is the same for all the 3 pools. And the alternative hypothesis is at least one of the 3 pools is different from the others. Now we have our null hypothesis. The next step for us to do is to kind of summarize the data set, which includes the mean, standard deviation, and the sample size for each group. So here for group A, the pool A, the mean temperature is 31, and the standard deviation is 0.551, and there's 20 measurements in this group. And for pool B, the mean is 37.2 with a standard deviation of 0.582. And for this group, it has 21 samples. And for group C, the mean is 41, and the standard deviation is 0.43. And for this one, it also has 20 measurements. And the total sample size is the sum of the sample size from the 3 groups, which is 61. Now let's build our own ANOVA table. So for this calculation, we'll need to calculate the sum of squares, degree of freedom, and the mean squares for the between groups variance and the within group variance. Then we can calculate the F ratio from MS group and the MS arrow. Then after we have the F value, then we can refer to the F distribution table to find out whether the p-value is smaller or larger than the alpha, which is the significant level. Okay, let's start our process. Now let's do the calculation of the SS group first. So here is the formula to calculate the SS group. To calculate the SS group, we will need the number of the number of measurements in each group, and the mean in each group, as well as the grand mean for the entire sample. So here is how the grand mean is calculated. So this one here is the mean of group A, and times the number of measurements in group A, which is 20. And here is the mean of group B times the number of measurements in group B. And so here is the mean of group C times the measurements in group C. And the sum of these is divided by the total number of measurements in the entire sample, which is 61. Then the calculated grand mean is 36.4. And to calculate the SS squared, we use the mean of group A minus the grand mean and squared it and times the sample size of group A, which is 20. And this part is for the group B, and this part is for the group C. And the calculated SS group is 1015.7. Next, let's calculate the degree of freedom for the group, which is k minus 1. In this case, k equal to 3. So the degree of freedom for the group is 2. And the mean square groups is calculated as SS group divided by degree of freedom group. So if we plug the numbers here, and it's 1015.7 divided by 2, so the mean square groups is 507.9. So we already have the first row of values calculated here. Now let's calculate the values for the arrow group. Okay. So the formula for the SS arrow is sigma dfi times si squared. So this is the degree of freedom within each group, which is ny minus 1. And this is the standard deviation for each group times 2 n squared. So it's also called the variance for the group. So it's like this is the value for the first group for the pool A and pool B and pool C, and we can calculate the sum of squares arrow as 16.1. And the degree of freedom for the arrow group is n minus k, where n is 61 in this case, and k equal to 3 in this case, and the df arrow is 58. Then the mean square arrow is just to divide SS arrow by df arrow. So it's 16.1 divided by 58. Then we get the mean squared arrow as 0.277. Now we have the variance for the group between groups and the variance within groups. So the total variance will be just the sum of these two. And the degree of freedom for the entire sample is n minus 1, which is 61 minus 1 is 60. Although we're not going to use this 2 value for our final calculation of the F ratio. So to calculate the F ratio is just the MS group divided by MS arrow. So it's 507.9 divided by 0.277. So the final calculated F ratio is 1834.7. Okay, now let's put this value into the ANOVA table. And then the final step we will need to do is to go to the F distribution table and find out our p-value. So to do so, I'll need to introduce the F distribution table, which is organized so you can look up the critical value of F for different within group and between group degree of freedom. The F distribution table will give like critical values of the F distribution at different significant level, which is alpha. And in most of the cases, what we use is 0.05. And to determine the critical value, the two most important parameter we'll need to know is the degree of freedom of the numerator and the degree of freedom of the denominator. So in our case, the numerator df is also the degree of freedom between groups, the df group, and the denominator degrees of freedom is also the degree of freedom within groups. So that's also the df arrow. So based on the df arrow and the df group, then you will be able to find a critical value from the F distribution table. And for example, here, the numerator degree of freedom is 9, and the denominator degree of freedom is 12. So which also means, so the df group is 9, and the df arrow is 12. And based on these two values, it will give you a critical F value of 2.8. And if your calculated F ratio value is larger than 2.8, and it will fall on this side, which means your p-value will be smaller than 0.05. However, if your F value is smaller than 0.28, so it will fall on this side, which means your p-value will be larger than 0.05. Here is the F distribution table at the significant level of 0.05. So the first column here is the denominator degree of freedom. And the first two rows here shows the numerator df, which is the df groups. And the denominator df is the df arrow. And for each denominator df and numerator df combination, you can find a significant, you can find a critical F value at the significant level of 0.05. For example, if our numerator df, the df group, is 5, and our denominator df, or the df arrow, is 20. So first we need to check this row here, and to check the column for the 5, and the value we will get is 2.71. Yeah, so this is our critical value for the numerator df as 5 and the denominator df as 20. And the next step for you to do is just to compare your calculated value to this critical value you get. Another thing you need to pay attention to is the denominator df goes all the way up to 200. And as the numbers go up, the changes between two significant values, the critical values, is really small. So here is just a summarize of the information from the F tables. So your numerator df is df group, or k-1, and the denominator df is the degree of freedom arrow, or n-1. And because the differences between the critical values of f become very small when n or k are very large, so the table tends to be condensed. And you can use the closest value for degree of freedom if your exact value is not on the table. Now let's back to our example. In our example, the calculated F is 1835, and the DF group is 2, and the DF arrow is 58. Now let's go to the F distribution table. For our case, the degree of freedom groups, the numerator DF is 2, so it's this column. And our degree of freedom arrow, the denominator DF is 58. So we can see in the table, we don't have a line for the 58. What we have here is just the line for the 50 and the 60. But we can see here, the value for the 50 and the value for the 60 is very close to each other. And because our value is 58 and is closer to 60, so the value at the column 2 for the 60 row, this one, will be our critical value to use. Okay, so the critical value we get is 3.15, and our calculated F value is 1835, which is far larger than 3.15. So now we're able to know the p-value is smaller than 0.05. And the conclusion we can get from this p-value is we can reject the null hypothesis. Therefore, at least one of the group has a population mean different from another group. So this will be our final conclusion. Here is just, let's finalize and complete our ANOVA table here with p-value less than 0.05. And the conclusion will be to reject the null hypothesis. Okay, now let's do a little bit more practice on the F tables. And based on these 4 different scenarios, let's calculate the DF group and the DF arrow. And also, based on these 2 values, let's go to the F table to find out the critical value. Then by comparing this critical value to the F value we provided, then let's draw a conclusion on whether P is smaller or larger than 0.05. I think you can pause here now and do your calculation and check the critical values in the F distribution table, and then you can continue playing after you are done. I'm going to show you the results in the next few slides. So let's start from the first example. In this one, it's the measurements on 30 people divided in 6 different groups. So the DF group will be K-1, which is 6 minus 1 is 5. And the DF arrow is 30 minus 6 is 42. And according to the F distribution table, it will give us a critical F value of 2.62, which is larger than our calculated F value, 1.9. So the p-value we get will be larger than 0.05. Now move to the next one. So in this case, we have 40 participants and 3 different groups. So the DF group is 3 minus 1, which is 2. And the DF arrow is 40 minus 3, it's 37. And from the from the distribution table, we will get the critical F value is between 3.23 to 3.32. And this value is also larger than the calculated F value, which is 2.4. So the p-value is larger than 0.05. Now the third one. In total, there are 28 measurements and divided into 4 equal groups. So DF group is 4 minus 1, which is 3. And the DF arrow is 28 minus 4, it's 24. And the critical value we can get is 3.01, which is smaller than the F, which is 6.1. So the p-value we can get is smaller than 0.05. For the final row here, there are 21 groups, and there are 10 people in each group. So in total, there are 21 times 10, which is 210 subjects in total, and 21 groups. So the DF group is 21 minus 1, which is 20. And the DF arrow is 210 minus 21 groups. It gives us 189 as the DF arrow. And when we go to the F distribution table, the critical F value we can get is between 1.62 to 1.68. And because our calculated F value is 3.2, which is larger than the critical value, then our p-value is smaller than 0.05. So here is another question based on the example, the last example in our previous slides. In that slides, we based on our calculation, the p-value we get for the scenario is smaller than 0.05. So what will be the conclusion we get based on the p-value? Yeah, you can pause and think about this question. I'm gonna give you the answer when you're back. So the correct answer is A. Because the p-value is less than 0.05, so we reject the null hypothesis. So the at least one mean in the groups is different from the others. So that's what we get based on the p-value. So here is just a link to a website which can calculate the exact p-value based on the F value, the calculated F value you get, and also the degree of freedom for the groups and the degree of freedom for the arrows. Basically, in this website, you just need to enter your calculated F value and your calculated DF group and DF arrow. It will automatically calculate the p-value, and you can just compare this calculated p-value to the alpha, which is 0.05. So if your p-value is less than 0.05, then we can reject the null hypothesis. And if it's larger than 0.05, then we fail to reject the null hypothesis. So this is just a source you can use to do some quick calculation on the p-value. Like other tests we learned in this class, for example, like chi-square test or t-test, there are certain assumptions of the ANOVA test which must be met for the test to be valid. So the first one is the samples must be randomly collected. And the second one is the sample must follow a normal distribution. And the third one is all groups must have equal variances. This one is a little bit complicated, so I won't get into too much detail here. For more information, you can go to the chapter on ANOVA in the textbook. To simplify, a rule of thumb here is the largest standard deviation among all groups cannot be larger than 2 times of the smallest standard deviation. Now let's do an ANOVA test together using another example. This time it's about caffeine and humans' memory. And this time I want you guys to do some calculations by yourself. Some previous studies have been found that caffeine intake may have an impact on humans' memory. So we did an example where 15 students were sampled and randomized into 3 groups with 5 people in each group. The first group was given a Coke, which contains 34 milligrams of caffeine. The second group received Tim Hortons coffee with a caffeine level of 100 milligrams. And the third group received the Jolt Cola, which contains 160 milligrams of caffeine. After drinking these beverages, the students completed a memory test. The results are shown as the number of words recorded from a list. Now let's take a look at the actual data. We have 3 groups here: the Coke group, the coffee group, and the Jolt group. In each group, there are 5 students, and the numbers are shown here are the number of words memorized by each student. Okay, so in this case, the explanatory variable, different types of drinks, is a categorical variable with more than 2 levels. And the response variable, the number of words recorded, is a numerical variable. Therefore, the test we should use in this scenario is ANOVA. You can pause here and think about what should be the null hypothesis in this case, and I'm going to show you in the next slide. In this example, the null hypothesis is the mean number of words recorded is the same for every beverage treatment group, or the mean number of words recorded is not different in groups defined by the beverage treatment. Now we have the null hypothesis. What we need to do next is to summarize the data in order to calculate the F ratio at the end. First, let's calculate the mean and standard deviation of each group. You can pause here and do your calculation. When you are done, you can continue playing. Okay, so here, the mean and standard deviation of each group is shown at the bottom of the table. So it's 8.8 for the Coke group, and it's 12.2 for the coffee group, and it's 13 for the Jolt group, and the standard deviation is 2.17 for the Coke group, and 1.79 for the coffee group, and 2.24 for the Jolt group. After we summarize the data, now we can start to fill in the blanks in the ANOVA table. We can start with calculating the SS group, which is the sum of square for the groups. And to do so, remember the formula we have before. First, we will need to know the grand mean or the overall mean. And here I give you a hint on how to do this calculation. So this one can be calculated as a weighted average of the means of the groups. So you can pause here and do your calculation. I'm going to show you the results in the next slide. So here is the results of the grand mean. So Y bar is 11.3. So here, 8.8 is the mean for the Coke group, and it times the number of subjects, which is 5. And here is the mean of the coffee group, and times the number of subjects, which is also 5. And the mean for the Jolt group is 13, and times 5. And the sum of these divided by 25, 15, which is the total number of subjects in the entire sample. And we get 11.3. So this is the grand mean of the entire sample. The next step is to calculate the SS group, the sum of squares. of the groups. I have the formula for the SS group here. It's the sigma ni times bracket yi bar minus y bar bracket squared. So here the ni is the number of sample in group I, and the yi bar is the mean in group I. So now you can do your calculation. I'm going to show you the results later. Here is the calculated SS group, which is 49.7. So you need to use the mean of the coffee group minus the grand mean, and you squared it and times the number of subjects in this group, which is 5. And for the coffee group, the 12.2 is the mean for this coffee group, and minus the grand mean 11.3 and squared times 5, which is the sample size in this group. And this part is the calculation for the George group. Finally, we get 49.7 for the SS group. Now in the ANOVA table, we have the SS group calculated as 49.7. So for us, the next step is to calculate the degree of freedom for the group and also the mean squares for the group. Here. So the degree of freedom of the group is calculated as k minus 1, which is 3 minus 1 equal to 2. Okay, then the next step we need to do is to calculate the mean squares group, which is calculated as SS groups divided by DF groups. Okay, so you can do your calculations on your side and pause here. I'm going to show you the numbers in the next slide. So here is the calculated value for the mean squares groups, which is 24.9. So now we have filling the first row of the ANOVA table, which is the variance between groups. And the next step for us is to calculate the within groups variance, which is the second row. And we can start with the calculation of the SS arrow. So here I show the formula to calculate the SS arrow and the degree of freedom arrow and the mean square arrow. So you can do the calculation on your side, and I'm going to show you the results in the next slide. Here is the calculated results. The SS arrow is 51.6, and the degree of freedom arrow is 12, and the mean square arrow is 4.3. And we put these numbers inside our table. And the next step, we can calculate the sum of square for the total and the degree of freedom for the total, although we're not going to use them. So this part is just the sum of these two. And this one is the n minus 1, which is 15 minus 1, so we get 14. Now, let's do the calculation for the F ratio. So it's estimated as the MS group divided by MS arrow. You can pause here and do the calculation on your side. Here is the final calculated value for the F ratio, which is 5.8. Now let's put this value into the F table. Okay, so we are almost in the final step. We have the calculated F value. Now we just need to go to the F distribution table and find the critical F value. So you can pause here and go to the F distribution table to find the critical F value. Here, we use the significant level, alpha is 0.05, and the degree of freedom for the numerator, also the degree of freedom for the groups is 2. And the degree of freedom of the denominator and also the degree of freedom of arrow is 12. So you can go to the F table to find the critical value. After go through the F distribution table, the critical value we got for this case is 3.89. We have a critical value as 3.89. Now we just need to decide if the p is larger or smaller than 0.05. Yeah, and because our calculated value is larger than 3.89, so the p-value will be smaller than 0.05. And now we know the p-value we calculated is less than 0.05. So what will be the final conclusion on the null hypothesis? You can pause here, and I'm gonna show you the results after you make your choice. So because our p-value is less than 0.05, then we should reject our null hypothesis. So this is the correct answer, option A. Now let's expand on the ANOVA test. Say we have performed our test and the p-value indicates we should reject the null hypothesis, which means at least one mean is different among all groups. What if we want to know which groups are different from which others? In order to solve this problem, what we can do here is to do a post hoc test. And the Tukey-Kramer test is a common one we always use. Usually we do the Tukey-Kramer test after we found variation among groups in ANOVA. And the Tukey-Kramer test is designed to compare the means between any two groups. Now let's see an example. As the background information for this example, trees and other plants are often connected by their roots, which allow them to exchange nutrition and other resources. In this study, they found the carbon transfer between birch and Douglas fir might have been influenced by the shading on them. 3 shading treatment groups were created, and each group had 5 samples. The net amount of carbon transferred between birch and fir was measured for each sample. The mean standard deviation for the 3 shading groups are listed in this table here. So for the deep shade group, the sample mean is 18.33 and the standard deviation is 6.98. For the partial shade group, the mean is 8.29 and the SD is 4.76. For the group with no shade, the mean is 5.21 and the standard deviation is 3. After we performed the ANOVA test, we found a p-value of 0.004, which is less than 0.05. So we reject the null hypothesis, and now we know at least one mean is different. Now, let's do the Tukey-Kramer test to find out which one or ones are different from the others. Since the Tukey-Kramer test compares the means between any two groups, the test has multiple null hypotheses, one each for each comparison. Here we can see for the first hypothesis, it's the mean of the first group. It's the same as the mean of the group 2. And the second one is the mean of the group 1. It's the same as group 3. And the mean of the group 2 is the same as group 3. You don't have to know the calculation process. You just need to understand how to read the results here. So let's see the first row of the table is comparing the mean of the deep shade group and the no shade group. And we can see the conclusion here is to reject the null hypothesis. So there is a significant difference between the mean of the deep shade group and the no shade group. For the second row is comparing the deep shade group and the partial shade group. And we also have the null hypothesis rejected. So these two are also significantly different. Now let's go to the third line. Is comparing the partial group and the no shade group. However, this time we see we failed to reject the null hypothesis. So there is no big difference between the means of these two groups. Here is another way how the results are presented. So the groups which cannot be distinguished are assigned the same letter. For example, here we can see the deep shade group was assigned the letter of A, while the partial shade group and the no shade group was assigned the letter B. So this means the mean of the deep shade group is significantly different from the partial shade group and the no shade group. However, because these two groups have the same letter assigned, so there's no big difference between the means of the partial shade group and the no shade group. Here is another imaginary example. The group in the middle, this one, cannot be distinguished from the first and the third group, even if the group 1 and group 3 are significantly different because they are assigned different letters. Okay, so this is the end of today's lecture. In this lecture, we cover ANOVA test, which is for the scenario where you have a numerical response variable and a categorical explanatory variable with more than 2 categories. In the real world, you don't have to worry too much about the calculation because the software does all. But you do need to know how to draw conclusions from the p-value you get. We also talk about the post-hoc test, what it does, and how to interpret the results. Next week, we're going to talk about the correlation and regression, which is used for 2 numerical variables. Take care and see you next week.